All right, so now what we're going to be talking about are electrons and the various ways that they can move, and then the different energy levels and how they actually exist within an atom. So the model that you guys are most familiar with is the Niels Bohr model. And what Niels Bohr came up with is that basically you have this nucleus. And around this nucleus are the electrons. And they go in these fixed energy levels. Okay, so you would possibly find an electron in the first energy level, in the second energy level, in the third energy level, but you'll never actually see them in the space in between, okay, because they have the fixed energy levels. So either an electron has this energy level for the first one, the second, or the third, but it can never actually have it ever in between, okay? So that's the one that you guys note, and then these electrons just orbit around and around and around. And this is a very simplistic model, which makes it a lot easier to utilize for a lot of different things that chemistry deals with. So that's kind of why we actually still use this in the current modern classroom. So what are these energy levels? First off, it's very nice for you guys to think of it as like rungs of a ladder. And the closer to the ground you are, the lower the amount of energy you have. So if we were to label this guy that I'm doing over here on the right, we have energy level 1, energy level 2, energy level 3. So energy level 1 has less energy than energy 2 or 3, and 3 has the most on this particular diagram. So let's say we have this electron, and it typically exists in the second energy level. This would be known as its ground state. The ground state is where an electron is typically found, how much energy it normally has. Well, what can happen is sometimes you add energy to an electron, either the form of heat or through electricity. And those are the two forms that we're going to be primarily using here. And when we do that, what we do is we add energy, and that electron absorbs the energy. When it absorbs that energy, it no longer has the right amount of energy to stay on the second energy level. So what's going to happen is it's going to jump. And it's going to do a leap that we call a quantum leap. And a quantum leap is beyond what we know in mechanical physics, so what you're actually familiar with in your everyday life. What happens in quantum physics is that this electron in the second energy level is able to instantly jump up to the third energy level without actually going through any of that space. So if you've ever seen like teleportation, like where it goes from one spot to another instantly, that's exactly what happens in reality with the electron, and that's called a quantum leap. So when we have these electrons that jump, okay, it goes from its ground state, which I'm going to say is at the second energy level, and it's able to jump up either to the third, depending on its energy amount that it absorbed, or the fourth. Okay, and it can keep going as depending on the energy. But what now it is it's known as it's in its excited state. And these electrons don't like to be in the excited state because they have too much energy for what they normally like to do. So what they do is they instantly release energy in the form of light, or photons as we know them. So they're known as photons or light to move back down to the ground state. So once again, it goes from a ground state electron, absorbs energy, does a quantum leap up to another energy level, becomes an excited state, does not like it, so releases that newly absorbed energy in the form of light or photon to go back to its ground state. So that's how the Bohr model actually works with releasing of light and energy levels. What we realize, though, is that the Bohr model is too simplistic, and that's not actually how electrons actually exist. What they do is they exist instead of perfect little orbits, they exist in this cloud-like state. So if we had an electron, and I took a time-lapse photo, what happens is that the time-lapse photo, the electron exists in this certain type of room, I guess you want to say, in this shape. This one we'll call the S shape, and you'll figure that out or understand in a little bit. But let's say 90% of the time that electron exists in that little spherical shape. Now 10% of the time it may be outside of it, so you'll notice that there's dots now being made outside of it, but most of the time, once again, it would be within this little vicinity, 90% of finding it within this shape exact area. And this is called the quantum mechanical model, or the electron cloud. So now we do not believe that electrons actually exist in these perfect little orbits. They kind of exist in this little given area. So with this, they have different amounts of energy associated with the different shapes that they can take on, or the different rooms that they exist in, the different energy levels that they have, and the where the direction that these sublevels or shapes take on. So we're going to go into these a little bit more, but what I'm going to do right now is go over the basics of them. So the quantum number is known as your energy level. You are going to need to have all of these known. Okay, so if I tell you energy level, you're going to tell me quantum number is the same thing. If I tell you 1s something, you'll tell me that 1 is the quantum number or the energy level. Then we've got sublevels. Sublevels I think of as the shapes. So what kind of a room do these electrons exist in? And there are the 4 different shapes that it can take on of S, P, D, F, and we'll show you those on the next slide of what they actually look like. And each one has a different amount of energy associated with them. S has the least, P has the second, then D, then F. As you get more intricate in the types of shapes that they have, there are more and more energy associated with them. And then atomic orbitals is the region where it's high probability of finding the electron. But what I always think of it as is the direction or the plane that your sublevel or shape is found on. So let's do an example so this becomes a little bit clearer. So we've got these different orbitals. First off, this is the S, or sublevels. This is the S one, and I always think of the S shape as a sphere. This has the least amount of energy associated with it. Then comes your P, which I always think of looks like a peanut. Okay, then you've got D. This is the only one that I couldn't come up with something clever. This looks like a clover to me, 4-leaf clover. And then we've got an F, and that looks like a flower. And it makes sense when you're looking at these. Obviously, S seems like a more simplistic shape than F, so it has less energy associated with it. And that is in actuality how it really is. So let's go a little bit more into this P orbital. So sometimes you might see a P or P sublevel, and let's just draw a P. Okay, so here's P, and right now it is on the y-axis. So what we would define this as is that its sublevel is P, and that it is atomic orbital is y. Okay, so that one would be the y one. Then we've got, let's say on this one, so this would be P sub x. And in Calc 3, you'll learn this, but there's actually a Z which comes out at us. It makes the world 3D. And there actually is a P sub Z. So for P, you have how many different types of atomic orbitals? You have P1, PZ, 2 of PX, and 3 of PY. So there's 3 different orbitals for the P. And D has 5 and F has 7, depending on their orientations, because they can rotate and stuff like that. All right, so what ended up happening is that scientists wanted to be able to figure out, hey, let's simplify this a little bit. Let's try to show where the electron's energies are associated. How high can we get up? How much energy is in the highest electron? How much is the energy is in the lowest? And what they did is they created this energy diagram, which looks like this. When you're reading it, it reads from the bottom up. The ones on the lowest, on the low end, are the lowest amount of energy. So 1S, 1 represents the energy level. S represents the sub-level, okay? And as you work your way up, you're getting more and more energy. So you kind of work your way. As you notice, okay, you actually go from 3P, so that's the 3rd energy level, up to the 4S, which is the 4th energy level with a spherical shape. And then you go to 3D, so you actually go back down in energy level. But because of the difference in shapes and the overlaps and stuff like that, S, which has this spherical shape, has a lower amount of energy for 4 than the 3D one, which has that 4-leaf clover shape. So it's not like it always goes energy levels, then sublevels. It doesn't go automatically in order. All right. So there are some rules, though, that you have to do when you are filling in these energy diagrams. There are 3. One is the Aufbau principle, and the Aufbau principle tells you that you have to build up. What that means is that you have to fill the lowest amount of energies first before you go up to the next amount of energies. Notice I didn't say energy levels because we had that 4S 3D thing, and you would fill up 4S because it has less energy associated with it than those 3D ones did. So you always fill up, the electrons will fill in the areas where with least amount of energy and build up to the greatest amount of energy. Then you've got the Pauli exclusion principle, and what that states is that electrons, when they are sharing the same atomic orbital, they need opposite spins. And how do you show an opposite spin? Is you draw an arrow. You can either draw a half arrow or a full arrow, one going up and one going down. So me looking at an energy diagram, this shows me that there are 2 electrons in that atomic orbital, and they are going opposite spins. Okay, so no 2 electrons can have the same quantum numbers, and that's why he tells about these different spins. Right now, we're not really going to have to worry about that, so don't really stress too much about that. All you really need to understand is that when 2 electrons are sharing the same atomic orbital, they need to have opposite spins. So there's one arrow, and then it goes the opposite way. I also draw half arrows like that, and that shows the different spins. That is perfectly acceptable too. So the next and the last rule is Hund's rule. So we had Aufbau, which means you fill up the low energies first. Then you've got Pauli, which means that the spins, if they are filling the same atomic orbital, they have to have opposite spins. And then now I'm going to be dealing with Hund's rule, which is where if you are in the same atomic orbital level or sublevel, what you want to do is you're going to fill up the electrons in each individual box first and then start partnering them up. Think about this as like your rooms that you would share with your siblings. If you had 3 rooms available and you had 3 siblings, most likely each one would want to be in their own room. You would never partner up and have 2 people sharing a room, whereas one whole room would be empty. Okay, so that's what Hund's rule says, is that you want to fill up all the same things on the same energy. Make sure every electron is spread out as much as possible, which makes sense because they all have negative charges, so they don't want to be by each other if possible. So spread them out as much as possible before you start partnering them up. So what we're going to try to do is do the energy diagram for phosphorus. Okay, and phosphorus has 15 electrons that we're going to need to account for. So this one, it has the first energy level, so I filled in my 2 electrons here. So now I'm going to just start going up till I get to 15. So it's 3, 4, 5, 6, 7. Notice because of Hund's rule, I haven't filled up the other ones yet, but 8, 9, 10. Notice that these are going opposite spins because of the Pauli exclusion principle. Now I'm 11, 12, 13, 14, 15. So once again, we're going to have these are known as 3 unpaired electrons. Why are they unpaired? Because they don't have a partner with them. And that's exactly what we want to happen, because according to Hunt, they said electrons want to be in separate ones if at all possible. So we're going to have 3 unpaired. Now the great part is that yes, these energy diagrams are very easy to fill in, and you'll realize that soon enough. But what's really cool about it is that you can do an abbreviated version even for this, and that's called the electron configuration. Okay? How do you do the electron configuration? You work from the low energies up, so it would be 1s. Okay, that's the energy level, that's the sublevel, and then how many electrons are found in there? Well, that would be 2. Now we got 2s. How many electrons are there? 2. Now we're going to fill in 2p. How many are there? 2, 4, 6. Now 3s, that would have 2. And then now we're going to do 3p. There's 1, 2, 3. So this is also telling me the exact same thing that this energy diagram did. It just accounts for where all of the electrons in phosphorus are located. We'll be practicing a lot more of these in class.